Yeah. Okay, I just started, just to let you know, I just started the recording, just in case I start making presentations soon. I am recording this meeting. I'm actually recording it 2 different ways to see if that'll actually make sure that the recording gets out there in time. I can hear some audio coming in from somebody other than me. Hello, is this Rob Quick?
Yes, it is.
Hi, Rob. How you doing today?
Good. I'm sorry, I just got in. I had a lot of difficulty getting through the firewall here at work.
That tends to happen, especially when we're trying to open up the meeting center, because sometimes it thinks that you're doing some sort of peer-to-peer sharing, and firewalls tend to want to block that. Okay, well, thank you very much.
I'm going to mute my mic right now.
Okay, thank you. All right, welcome everyone to the September meeting of the Stamping and Dies Tech Group. Again, this is the Stamping and Dies Tech Group. We are a subset of the forming and fabricating community inside of SME.org. SME, formerly known as the Society of Manufacturing Engineers. We are a professional society, and it is our goal inside this technical group to pull together all of the SME member professionals who are interested in sheet metal stamping and dies, and to share our knowledge, our expertise, and to just get a richer discussion specifically on metal forming and sheet metal and stamping. Some of you who are joining us today in today's meeting, maybe you're not specifically in stamping and dies, but in some other mode of metal forming. We welcome you, and of course we do try to, as much as possible, consider how we're going to broaden the reach of these meetings so that we can see how other manufacturing disciplines are affected by or affect the stamping and dies technical community. But if you can hear me, you've already successfully logged on. I do have the telephone information. One of the things that I normally do when we start each one of these meetings is we do remind people of some upcoming events and meetings inside of sheet metal stamping and metal forming. It is my understanding that the PMA is going to be having an event. Let's see, their event is in October 7th. The Precision Metal Forming Society is having their servo press technology experience. That was mentioned to us by one of our frequent phone-in members of this technical group as something that they're presenting at and sharing their expertise and their knowledge in metal forming. Something new on the calendar. Today we are going to be talking about hot forming. That's the topic that was determined for this month's materials-based topic, so I will talk a little bit about hot stamping or hot forming. I do want to mention, though, in October there is a seminar, or I should say an in-depth training session offered by a company called Grundig. And Grundig is a German company. They were most famous at one time for making radio equipment. They were a long-time competitor of Motorola. And Grundig is having their Grundig Academy here in Troy, Michigan, with an intensive training for the simulation of hot forming. And that would allow people who don't have previous metal forming simulation experience, they're new to the topic of metal forming simulation, or they're new to the topic of hot stamping, and through Grundig Academy there is a possibility to take a 2-day-long training class that would actually put your hands on metal forming simulation software and teach you a little bit more about how one simulates and engineers the process for hot stamping that we'll be talking about a little bit later today. One thing notable, you notice I might have I call this Module B in the Grundig Academy training. They actually have a curriculum that they've put together in conjunction with several steel manufacturers and automotive manufacturers, and this curriculum is recognized by a few key automotive OEMs as the equivalent of a master's degree in materials or mechanical engineering if you were looking for a job relevant to hot stamping, hot forming at that company. So if you are interested in learning more about hot forming or finding a job in hot forming, etc., take a look at Grundig Academy. I have attached here the website. That's www.hotforming-academy.com, and that is the Grundig Academy, and they are having, I believe it's a 4-module session, modules A through D, that would give you the possibility of learning more about hot forming and actually get a certificate and certified through the Grundig Academy, which has professional benefits for you outside of just taking the class and your own knowledge. But there are companies that would recognize that in job search and on your resume as the equivalent of a master's degree. Also, hopefully none of you are a stranger to the idea that in November we will be gathering down in Atlanta, Georgia for FabTech 2014. FabTech 2014 will be running November 11th through the 13th down in Atlanta at, I believe, the World Congress and Expo Center, and there other members of SME, as well as the Forming and Fabric, the PMA, Precision Metal Forming Association, the FMA, the Fabricators Manufacturing Association, AWS, as well as I believe there's a coating and heat treating society that meet there as well, to talk about pretty much all things metal forming, metal fabricating, from the forming of the materials to the materials themselves, manufacturing of the tools, assembly, soup to nuts, everything you would want to know about metal forming and fabrication at FabTech 2014. At that, I have the pleasure of having 2 of my technical presentations were accepted by the folks at FabTech to be technical presentations that we will be offering in part of as part of the educational track. November 12th, I believe the 8 to 10 o'clock session, and then the 10:30 to 12:30 sessions. I will be giving a introduction to metal forming analysis. That would include physical analysis of formability, as well as virtual analysis and computer analysis of formability, as well as a session specifically on how to measure, predict, and correct sheet metal springback. And that's all happening at FabTech, again at the World Expo. I'm going to open up everyone's microphone right now and just ask the question I ask every month at this time. If anybody else knows of any other relevant events that would be worthwhile and meaningful for our members to join. All right, so your mics are all up. Anybody know of any other upcoming events that people could still sign up for and attend if they're interested in learning?
This is Dean. Couple things in expansion of that. The Servo Press Technology in October, which is a face-to-face event down here in Tennessee. There's also this Thursday and next Thursday, PMA is having a free WebEx event where you can call in and hear about that technology. I can't remember if Alton is doing one, Tyler. Alton is doing that also, but I know he's doing 1 or 2 of them. And then there's a free OSHA safety seminar that Link puts on in October, and that's the last one we do this year. So if anyone's interested in any of those, they're available.
And when in October was that?
Let's see here. The event in October is. Give me 1 second here. It looks like it's October 13th through the 15th.
October 13th through the 15th in Nashville.
Yep.
Okay. I was just typing that in the chat window. Hopefully that still gets recorded to the meeting recording, I believe. So, right, upcoming events, you said that this Thursday and next Thursday there is a PMA free webinar series. So if people go to metalforming.com, I believe, is the website for the PMA, and they'd be able to probably do a search to find that free webinar series. And that's still on the topic of the servo presses, right? There's kind of a teaser for their live events, right? And then you mentioned October 13th through the 15th, a Links Systems safety seminar in Nashville, Tennessee.
OSHA, yeah, OSHA press safety seminar.
All right. Good stuff. Okay. Then let's see. Today we are doing the topic is going to be hot stamping. I'll be giving a little primer on hot stamping technology, a little bit of why we're doing it, talk about the materials a bit, the manufacturing environment, engineering through simulation and implementation. Bob Strasser is one of our callers today, and in October he is going to be giving us a introduction to stretch forming. And those of you who are not familiar with stretch forming, this is an opportunity for you to learn a bit more about this other way of making metal into those shapes that we need in order to make our products, used in different industries to put metal into new shapes and make new products. So very pertinent for those of us in our technical group. In November, we still have a press room topic available. That is going to be during FabTech. Unfortunately, I won't get to do what I did last year, which was I actually ran the meeting from my trade show booth and was able to walk around with the webcam and stuff and do a little bit of exploring of the show floor. Unfortunately, it's going to be right during my educational session. So we will be having a meeting in November coincident with FabTech. And in December, we will be having our kind of our year in review, and I hold that topic, kind of general topic, open if we want to talk about education, professional development, and other topics such as that in the December meeting. But of course, if any of you who are on today's call are experts at or know that your company has innovative or beneficial technology and information to share regarding metal forming, sheet metal stamping, and dies, let me know, and we can put you on the calendar regardless of what we've set as our editorial focus for a given month. If you guys have a hot topic and you want to share that with us, either between now and the end of the year or anytime in 2015, be sure to let me know. I've put my email down at the bottom of this slide. That's kam.consultant@gmail.com, or you can email my co-chair, Breanne Roebuck, at broebuck@kent.edu, and let us know what your topic would be, and we'd be happy to find a slot for you in our presentation calendar, because we really do want to just expand this free opportunity for shameless self-promotion of whatever it is you guys do, as well as very selfish motivation of I want to learn more about technology, and line us up, tell us who you know is a good speaker or knowledgeable on a given topic, and we'll see if we can't rope them into doing a presentation, and that way you can get what you want, which is the new knowledge and information that's beneficial to you and your company. So we do kind of follow a relatively repeating structure just to make it easier for scheduling. So each year we're going to have 1 month where we talk about, yeah. Doug, did you have something you were going to add?
Oh, I'm sorry. I thought I was on mute.
Oh, no, that's okay.
I would ask, it'd be interesting to see how 3D printing might be affecting tooling, because they've now come out with a lot of metal 3D printing directly into metal, and that could potentially have a big impact on tooling.
Yeah, there's a couple things that I've really wanted to take a look at 3D printing for. Two reasons. One of them is that 3D printing and additive manufacturing absolutely are having an impact on metal forming and stamping. In two specific places I've seen it. In one place I've seen that they are doing additive manufacturing or laser sintering of complete tools that are being used for sheet hydroforming, and I know the guys over at this company that does that type of 3D printing. I could get a hold of them and see if they would be willing to make a presentation on that. The guys at Beckwood Press and at Stratasys. Another place that I've seen it is in Germany. The Frauenfelder Institute actually has a robotic 3D additive welding machine that I've seen that was able to do die repairs and die hardening of larger than what would normally fit even in those large format 3D printers that they have at IMTS. They can just roll this robot up to it, and this robot was essentially doing a spraying of powder metal with a high precision laser, and was able to do weld repair to a much higher degree of accuracy and quality than even very skillful people with hard weld rod were able to do for these die repairs. So there's several different areas where additive manufacturing and 3D printing and technology is interesting. You know what? I'm going to see if I can't find anybody who would be able to talk to us about that in November. It would be that would be a great topic. So if we can get a hold of somebody in November who would want to do that, that wouldn't be a bad opportunity. Otherwise, next year we have plenty of slots where that could come into place, because we could slot that under design and engineering. We can slot that under material topics. We can slot that under topics in forming and fabricating. That fits just about anywhere in my editorial calendar. So, good suggestion. Thank you, Doug. What other questions or suggestions? Okay, thank you. So again, maybe you don't have anything that you would like to request now, but do remember, anytime something comes up, or you read a great magazine article, or you hear something and you want to learn more about it, always feel free to send me or Brianne an email and just say, hey, it just occurred to me, I read an article in a magazine about a certain topic. Feel free to send us that idea. We'd love to hear from you, our members, as often and as frequent as you're willing to share information with us. So go ahead and feel free to contact us at any time. I also want to remind everyone that inside of SME we still do have a specific website for our individual tech group, whose address I've just circled on the top of this slide at i.sme.org, Stamping and Dies Tech Group, all spelled out with no spaces or special characters. And if you put in that website address, you will find a website we've put together just for the Stamping and Dies Tech Group. There I've put in some very basic educational resources that have been shared with us over the years through people who've made presentations. I keep an archive of the meeting presentations there. If someone gives us the PowerPoint that they presented during that day, I'll archive it there. At least a viewer to view those slides, etc. We do have a discussions area where our members can ask other members if they know how to solve a problem or if they have information on a particular issue. There's also our blogs and apparently my slightly out-of-date event calendar, because somehow or another I failed to put that today's meeting on that event calendar. So I'll have to expand that and make sure that that's all up to date. But please do use that very valuable resource for keeping in touch with us inside the Stamping and Dies Tech Group, but as well as other members inside of SME. All right. Today's technical topic is hot stamping, and to tell you the honest truth, I'm still feel like I'm very much a neophyte at hot stamping, and one of the reasons why I volunteered to do this topic is that I have to start doing bigger training classes myself on delivering training classes on hot stamping. So I wanted a little bit more practice and familiarity with the content materials, so I don't profess to be an expert at hot stamping any more so than I am a normal self-proclaimed die expert. So this is what I know and have learned about hot stamping recently. If there's something that you guys know or want to share with me, please feel free to chime in at any time. All right. When it comes to hot forming and hot stamping, one of the first things that we could talk about is why do we do it. One of the big things is that we have the of course the safety standards that we're trying to achieve. We want to make our cars safer, our vehicles safer for the passengers. So in these two pictures right here, you can see in these two examples of one of them is a front impact with an offset, the other one's a direct front impact, and you can see really significant incursion into the passenger compartment. So these would have been very potentially deadly and certainly injurious car accidents. However, if you look at this picture at the top, you can see that that front door barely looks like it's got any damage at all. Very little intrusion into the passenger compartment. And that's one of the big pressures behind using hot forming technology. And one of the reasons why we're using more and more hot forming technology is we're trying to deal with the seeming contradiction that we have between the fact that we want to make all of the cars lighter in order to reduce our CO2 emissions and drive down or increase the fuel economy and reduce our CO2 output. Right? So that certainly does make making the cars lighter more important. But of course, we do have the fact that our vehicles are getting more and more complex. The shape of the vehicles, the content of the vehicles, the safety that we're trying to achieve are all increasing the complexity of the types of parts that we have been making and will be asked to make in the future. So hot forming is really something we're trying to do to address that contradiction of how do I make it lighter, but of course make it stronger and have more function, right? And we're using this new material of boron hot stamping steel to address that. Right, so in order to resolve that contradiction, we are using increased lightweight alloys. We are seeing, people going back to aluminum for the Ford F-150 is the all aluminum truck body. That was done to maintain the strength and stiffness integrity that Ford wanted in their F-150 while still making a lighter vehicle and safe vehicle in order to get better fuel economy. So that all aluminum body of the F-150 and frame was certainly an attempt to go for lightweight alloys. However, one of the problems with aluminum is that aluminum is still very CO2 intensive, and that means that overall, if you start making a high aluminum fleet, you'll still overall have a relatively large CO2 footprint. And that's one of the reasons and one of the things behind this increased use of high strength, ultra high strength, and advanced high strength steels is to ensure that we're getting strong lightweight vehicles that are safe and offer great integrity, however do not necessarily increase the CO2 footprint of that particular vehicle. Right, so this is one way that we're trying to do it, is material with better strength at a reduced thickness. However, this does have a kind of a double impact on our ability to deform the material. As you go to stronger materials, Stronger materials have the tendency to resist the desirable deformation that we're trying to apply when we're sheet metal stamping or stretch forming that material, right? Because the whole reason we wanted to buy the high strength material is so that it resists the undesirable deformation in that front impact or that offset frontal impact. However, it's going to also mean that that material is going to inherently want to avoid the deformation that we might be trying to apply in a sheet metal stamping die. Right? And you can't necessarily have it both ways. Can you have a material that resists undesirable deformation but accepts what we think of as desirable deformation? And generally, I have to say, well, no, the material cannot tell the difference between what is desirable deformation and undesirable deformation. Hot forming and hot stamping is a way around that, because that is using temperature and heating that material up is a way that we're differentiating the desirable deformation that we're doing in the hot stamping operation from the undesirable deformation, which would be the deformation in ambient temperature of a vehicle in crash. Other challenges raised by trying to go to these advanced high-strength materials and increased strength materials, not only are stronger materials typically more difficult to form, right? They have lower forming limits or formability limits, but they also tend to have greater amounts of spring back. Right? So as we've tried to introduce these lightweight vehicle construction, whether it's high-strength steel or whether it's aluminum, is that in both high-strength steel and aluminum we do see a greater amount of overall spring back. And that makes it very difficult for us to achieve our dimensional accuracy goals, our PPAP goals. Right? It doesn't matter if I can make the part, if I can't make it dimensionally accurate to the right size and shape and tolerance, that new strong component or lightweight component doesn't do me any good. So these are the challenges that we're using hot stamping and hot forming to try to address. When we talk about hot forming and hot stamping these materials, we're usually talking about one very specific type of material that you might call boron steel. And I've also seen that steel called out with a numerical designation. Let me make sure I get this right. 22 MnB5. That would be this boron steel material whose chemical composition I have in this little table at the bottom of this slide. Right? So boron steel is a high carbon steel. It's got a significant amount more carbon than would a typical stamping steel. When we think about mild steel and a draw quality, we're usually talking about material that has a carbon by weight percentage at 0.08 or below. Right? If you ever hear people talk about steel, and maybe they've talked about steel in terms of the SAE designation, 1008 steel or 1010 steel. When you talk about 1008 steel, that 08 represents the maximum allowable carbon by weight in that material. So when we look at this hot forming steel, we're talking about steel with 4 times as much carbon, at least, more than your typical mild steel. Significant other things that you'll see is that there's a significant amount of manganese, right? That's Mn. The element manganese, we're seeing 1% of that material weight of the Mn. That's why we're calling it out in that material name. And there is this trace amount of boron. And this trace amount of boron really does have a profound effect on this material's behavior. And what happens with this material is that when this material comes from the mill, its non-hardened strength characteristic puts it in this range on the sheet steel, what people call the banana chart, that it has a range of available strengths at room temperature from the mill, somewhere between 500 and 750 megapascals in strength. That'd be somewhere around 35 to 50 ksi tensile strength at room temperature without this hardening. Then what happens is that you actually, and you can see that it's strong material, but it has a relatively low amount of overall elongation. That this material, while it has a very high strength, you might be lucky if you could deform it 10 to 15% before it fractured and failed. So these are materials that have relatively low amounts of natural ductility, natural deformability. However, when you heat these materials to 900 degrees Celsius, what happens is that material now becomes highly deformable, and it deforms quite well at these high temperatures, and now you can see 50 to 60% elongation of that material inside of the tool. And that's pretty good. That means that we can form even more complex shapes than we normally would use interstitial free or extra deep draw quality to form without causing a fracture or a failure in the material. But what's really cool about this idea of hot forming these specific grades of boron steels is that when you cool and quench that material, the material ends up in many cases significantly stronger than it was even coming out of the mill. Now that's not true for every other grade of steel that you might think of, right? You can't do this trick of hot forming the material with plain 1008 1010 steel. If you take 1008 1010 steel and heat it up to 900 degrees Celsius and then form it and then cool it, that material is going to come back to you in an annealed state, a softened state, and that material is going to be less strong and less structurally sound than it was when it came off of the cold rolling mill. That material would have very much a hot rolled quality to it, and it would lose a lot of the strength and characteristics that we like in our mild steels. However, this boron steel, when you heat it and cool it in this manner, you can end up with a material that is up to 50% stronger than the material was when we bought it from the mill. So we're adding value to the material in two different ways when we're doing this hot stamping. We're adding value by making it take on a new shape, and we're adding value by making the material stronger than it was when we first bought it. So that's a double dip as far as value add manufacturing processes. It's stronger and it's in the product shape. So what we see is for these materials, again, very much a similar chart that we had just on the previous illustration. But what's interesting about this one is this illustration provided by Audi showing the content that we have of the high-strength steel inside of this A3 vehicle model. You can see that we're using regular mild steel for components like the cowl, the wheelhouse, the body in white parts of the panel that are not vehicle that are not structural. However, these engine compartments are using this high strength advanced high strength materials, and we can see hot forming materials in the A pillar, in the B pillar, in the impact beam across the width of the car, in the firewall. All of these areas where we want this very high amount of strength to make sure that the passenger compartment is not having intrusion during an impact, we can see people using these high strength steels. Now this is all because of the metallurgical effect of, some people might call this the nose diagram, but this is the time temperature characteristics of these high carbon boron steels. And what happens is that when you heat the material up to this higher temperature and then allow it to cool, if you let the material cool slowly, the material is going to form a certain kind of microstructure whether it's ferrite or pearlite or austenite. Right? These are the microstructures of common carbon steels. However, if we take that material up to temperature and we're able to quench it in a rapid enough sequence, we're able to bring that material into a characteristic that we call martensite. And martensite is a microstructure common to these high carbon materials that is much stronger and has higher strength than we would expect in a mild steel that was a ferritic or austenitic microstructure. So it's very desirable with this hot forming to heat the material up to this wonderful temperature around 900 degrees and then cool it and quench it pretty rapidly in order to force this martensite microstructure to form in the material without seeing the microstructure pass through different phases or different types of microstructure. And that's the reason and that's the benefit for using these hot stamped, hot forming boron materials. So when we think about hot forming, there's two different ways you can think of these hot forming materials. Another term for hot forming would be this term that we call press hardening. Right, so same thing if you hear people talk about press hardened materials, die hardened materials, they're talking about the same thing that I am right now. They're taking a blank of material, they're heating it up, forming it, and during that forming operation, quenching it to this martensitic microstructure, martensitic phase of material. There's two schools of thought when you think about this hot stamping. There's what we call direct hot forming, and there's indirect hot forming. Direct hot forming starts by taking the coil of material, unrolling it, creating your blank, taking that flat blank and passing it through a furnace to heat it up very uniformly to a temperature around 950 degrees Celsius, loading it into the stamping die, and inside of the die not only deforming the material, but as we're deforming it, also cool it and quench it down to ambient temperature, right? Something in the ballpark of 200 to 80 degrees C, right? When you get this material down into the range of 200 degrees C to 80 degrees C, you've already cooled it sufficiently that it's going to have the appropriate microstructure. Then potentially you could use a robot to gingerly unload that blank, let it go down to the conveyor belt so that it can get racked, or bring it to another station for laser cutting, laser trimming. Right, this is what we would call direct press hardening or direct hot forming. Indirect hot forming starts off with the same operation, but instead of going directly from the blanking operation into the furnace, you can actually form that material some of the way, partially, at room temperature. That's going to allow you to make a slightly deeper part without necessarily having a high degree of localized thinning. Right? One of the problems with forming these materials at such high temperatures when we do this direct hot forming is the fact that any thinning that does happen tends to be highly localized. Right? The material is heated up and it's very ductile at that point. And what will happen is that the thinning can get localized maybe in ways that are slightly undesirable. If we do the preforming at ambient temperature initially, that allows us to do a little bit of initial stretching of the material and hopefully be able to maintain a relative uniformity or at least less localized thinning behavior. Then we can put it through the furnace. So take the preformed thing and now heat it up in those furnaces to 950 degrees C. Then stamp it even more in this temperature controlled die in order to quench it, and then go to the laser cutting. And that would be indirect hot forming. So we can see that a variety of manufacturers. Here's a picture provided by Volkswagen for the Volkswagen Passat. Their use of press-hardened materials on their most recent Volkswagen Passat allowed them to reduce, on average, most of their sheet metal thicknesses of these parts that are highlighted in red have each been reduced by about 0.2 millimeters in thickness. And that meant also that we could reduce the overall number of parts. They're able to take what used to be a stamping plus a reinforcement and replace that two different stampings, two different parts in the assembly, with a single stamping that is press hardened. That reduced the overall number of forming operations and therefore reduces the amount of tooling. And if you reduce the amount of tools, then presumably you are driving down, in one aspect, the manufacturing cost. They were able to do this and in the meantime achieve an increase in overall part stiffness, because now if we have fewer number of parts in our assembly, the assembly is more integral and therefore stiffer. And of course an overall stronger component, because we've achieved a stronger component while reducing its mass. And that has very positive effects on passenger and vehicle safety. All right, so here are some other parts that were used. Again, that was the Volkswagen Passat, but there are components that you might see people hot stamping. Here is the tunnel. It used to be a single component with two reinforcements on the outer, two reinforcements inside, which is now a single stamping. 5 kilograms, that's a 10-pound reduction in the assembly. And we've seen in this example a B-pillar. The B-pillar used to be the B-pillar itself, a B-pillar inner, a B-pillar reinforcement, and then reinforcements for the pillar, the hinge, and the latch areas. And of course, by reducing those to just 2 hot formed components, we saw also there 4 kilogram reduction in overall vehicle mass. Similarly, door sills, roof panels and roof bows, B-pillars, tunnels, the firewall base mount and the subplate at the front of the passenger compartment, all candidates for this hot stamping. So we are seeing an increased amount of content in our vehicles of this hot stamped material. So it is a technology that is relatively well accepted and certainly proliferating throughout the stamping industries. Just have a quick picture here for you of this is the blank that is red hot. So that's the blank coming out of the furnace. The furnace would have been back to the left of this illustration, and the press and the die are probably going, oh no, here's the furnace, excuse me, drawing it sideways. There's the furnace, right? So the material came out this way out of the furnace. Here it is getting picked up after coming out of the furnace, and it's going to go this way into the stamping operation. All right, that is red hot, and that material at that temperature is above the crystallization temperature of the steel. So when you bring that material to that temperature, 950 degrees Celsius, 850 degrees Celsius, that material is a superheated liquid, right? It's or excuse me, a supercooled liquid. That material is solid enough to have form and shape and to be picked up, but its crystal structure is still relatively undefined. And it's not until that material starts to cool that we see the individual crystals or grains of the material set up in whatever the microstructure of that material is. So this material is highly pliable, highly deformable, but how it still has not yet decided what kind of material it's going to be once it cools to room temperature, because that depends on how we cool it. So when we take this idea of the direct hot forming process, we take that boron steel, we take it from room temperature to 950 degrees C in the furnace, and that heats that material up to its austenitic microstructure, right? That's the relatively amorphous, not fully formed grains or crystal structure microstructure. We form it inside of the die, and you'll notice I have all these little blue circles inside my illustration. Each one of those represents a liquid-filled cooling channel. Right? So this die is going to be piped, and it's going to have fluids passing through that die trying to maintain a particular temperature. And that way, when we close the die on the material is getting deformed, and the material is quenching in the meantime. So normally what will happen is you put the blank in, it takes 1 second, maybe 1.5 seconds to close the die, and then the die is going to stay closed, maybe dwelling at the bottom for, I don't know, 3, 5, maybe even 6 seconds, cooling and quenching at the bottom of the stroke. And as that's happening, the material's microstructure is going from this 950 degree austenitic microstructure possibly towards martensite or bainite or ferrite microstructure, and achieving certain yield strength and tensile strength characteristics. Some of the things that we're doing with these hot forming and hot stamping dies is that you can take the die and you can actually, in this illustration you'll see that I have one area that is shaded blue and I have another area shaded red. And what you can do is you can have maybe one area of the tool is being held at 400, 450 degrees Celsius, and the other tool is being held at 80 degrees Celsius. When you take the big superheated blank and you close it inside of a die that has these two different heating zones, what you're going to end up with is a different rate of cooling in the top half of that panel compared to the bottom half of that panel. And by changing the quenching characteristics, we get different material characteristics as we form this panel. So this is something that people might use the term tailor tempered. So tailored, like the guy who fixes your pants or your shirts. Tailored tempering allows us to very specifically control the material parameters, the material properties of the finished product by controlling the temperature at which this material quenches. So if I quench just the top part of this B pillar at 80 degrees C and I held the lower part of the die at 400 degrees Celsius, what will happen is that the lower part of the die would B pillar would not form this martensite. It would form more ferrite, more bainite in its microstructure, and therefore it would not have the super strong 1000 megapascal finished yield strength. It would finish up in strength more like what the material's original strength was when we received it from the steel mill. This material at the top, where we're quenching it to that 80 degrees C using this very cool tool, that's going to form a higher degree of this martensite, and that top of the B pillar would presumably be all at this martensitic microstructure and achieving that 1000 megapascal yield strength. So here's an illustration of a part that was produced specifically for a simulation benchmark study by an organization called Numisheet. And you can see here there's that blank. That blank's still red hot, and you'll notice that it's touching at the top of that of the die, right about midway through that B pillar, and it's also resting a little bit here at the bottom. And as soon as that die starts making contact with the sheet metal, the die is going to start acting like a heat sink for the material, drawing out some of that heat, causing it to cool or quench maybe a little bit earlier than was planned. And therefore, when we talk about this hot stamping, it's really we've really seen that this idea of hot stamping, hot forming is something that's going to be very reliant on our ability to engineer and mathematically simulate these forming operations in order to assure that we get the product characteristics that we finally wanted. Because it is possible that this early contact in these different areas of the blank, or even where we're holding it with whatever robot or automations loading that blank in, any initial contact could cause the material to cool at a different rate and not quite get the material properties that we were aiming for. Here's another illustration. These are photos of actual dies that were provided by Braun Cartech, but you can see here, this shows very clearly how that heating channel is distributed inside of our casting. Right, so inside our casting, this is a punch for what could be one of those tunnels from the front of the vehicle for a rear-wheel drive vehicle. This is the tunnel, and you can see here that the die post is pretty much a solid tool, except for this pattern of cooling channels that had to be designed and piped through the tool in order to help maintain that temperature. Here's a CAD illustration showing how we might have to design our tools a little bit differently in order to assure that we have the individual heating channels, and maybe if we're heating one part of the die differently than the other, it creates a very interesting design challenge of how do we make sure that one half of the die perhaps is held at one temperature while the other half of the die is held at another temperature. Here's an example of this is a photo of a part in that indirect hot forming. You can see that this part is coming out of the furnace red hot, and it already has some product shape applied to it. So in this case, this was indirect hot forming. They did some room temperature deformation of the part at ambient or room temperature. Then it went through the furnace to get heated up to the appropriate temperature, and then hot formed and additionally quenched and cooled in that environment. And that gives you perhaps the ability to form even more sophisticated, more complicated shapes than we would have achieved if we just did it in one hit. So the thing that happens is that as we start looking at this type of deformation, it adds a new layer, a new level of complexity to our metal forming operations. Right? We are going to end up having to understand that temperature is now an additional process parameter, one that we'll have to plan for and try to control and try to make sure that we can predict how the temperature is going to affect this forming operation and the product performance. So that means that we have to have material characteristics mapped out for that part at different temperatures that we might see throughout the forming operation. So that means a much more complicated methodology of testing our material as it comes in before it comes into our mill, and the ability to predict how does that material behave stress and strain wise at 800 degrees Celsius compared to 500 degrees Celsius. We also have to know not only how do the different temperatures behave, but material also has different strain rates. The faster it stretches compared to being stretched slowly, we do see different characteristics between the stress of the material and its strain, and therefore another complexity of our forming operation in order to mathematically model it. Here's some discussion on this idea of tailored tempering. I mentioned it briefly before. Tailored tempering, perhaps for this particular B-pillar, we wanted tailored tempered because at the bottom portion of the B-pillar compared to the top, we want different overall tensile and yield strengths in order to get different characteristics of the finished part. So in this case, the B-pillar, they quenched the B-pillar at the top. That's going to form a lot of that martensite microstructure. That's going to be the strongest, highest strength material that this B-pillar is ever going to see. Then there's going to be a little bit of a transition zone to the material that is allowed to cool or quench slowly. So the die at the bottom portion of this B-pillar is being maintained at around 400 degrees Celsius. And by holding that die warmer during the forming operation, we ensure that its microstructure is different than the top half, which is being cooled to 80 degrees Celsius. And that means that we're going to have a much higher strength material at the end of the forming operation for this top part of the B pillar, and then a much lower overall yield strength and tensile strength of the lower portion of the B pillar. And that was engineered for and designed in order to give a certain product performance for that B pillar that was selected by the structural or product engineer. So any of that material that is cooled very quickly forms martensite. The martensite grain structure is a very small grain. Those grains are having a different crystal structure that lends them a very high strength characteristic. If you cool the material a little bit slower, now you don't have 100% martensite. Maybe you end up with 99% martensite, 1% bainite, and that's going to give you a different characteristic and finished part. And then if you cool this at a much slower cooling rate by holding that die a little bit warmer, then you're going to have maybe only 90% martensite and 10% bainite. And that material is going to end up being, as far as its strength, closer to that mil spec original strength of the material, as opposed to being that tempered, highly quenched strength that we get when we were talking about the martensite. And you can see in simulation what we want to validate for our product engineers. We want to prove to them that the area that they designed to be 100% martensite did in fact achieve all of the strength that we were targeting. So the top part of this little pillar reinforcement I'm showing here has 100% martensite in this portion of the B pillar, or this is an A pillar, excuse me. But you can also notice that there's lower percentages of martensite. In this purple area, we're seeing martensite levels as low as 10%. So that material is going to be more like the original strength of the mild steel, of the not the mild steel, but of the steel directly from the stamping mill, the coil mill. It's not going to have that value-added quenching characteristic of being increased in strength. But you'll also notice a manufacturing-induced difference that we recognize, that perhaps in these two areas I just circled, maybe those two areas were areas where had early contact with the die during the forming operation. Those were, in fact, in this simulation that I ran, I had spring-loaded pads to support the blank prior to closing the tool in this operation. And where the blank was resting on this tool, it was acting as a heat sink, and it was drawing that heat out of the tool at a faster rate than did the rest of this A pillar, where we have some ability to put cooling channels or heating channels through the die in order to maintain the 400 degrees Celsius temperature. So the rest of this A pillar was being maintained at 400 degrees C, except for the little spring-loaded pads that were controlling this blank's orientation during the loading. And what happened is that we ended up with areas having more martensite than perhaps people might have planned for. And what that means is that these two areas are going to be stronger than the areas adjacent to them. And that could lead to maybe assembly problems, or that could lead to a difference in product performance that they didn't perhaps foresee or plan for. And you can see we also will not only measure and try to predict that microstructure, but also show what is the hardness of the material, right? The strength and the stress of the material relevant and being measured in terms of Vickers hardness. What is the strength of the material in these areas? And again, where I see this orange coloring, those are materials that, because of their martensite purity, their martensite content, are very high in the hardness scale. And these areas where I had my pads were a little bit lower in the overall hardness scale, but still significantly harder and stronger than the areas next to them, which are in these blue or aquamarine shades. So it's very important to validate our assumptions in the manufacturing and product design process. And the way that we're doing that these days is through metal forming simulation. And that's about what I think we can squeeze into our conversation today. I'm going to open the mics back up. I've been rambling on for some time. What questions do we have regarding this this hot stamping and hot stamping technology? Are you guys still awake?
Yeah, I'm here. Hey, it's Dean. I had a question for you regarding some of the challenges that you've seen in the actual tooling once you get into some of this hot stamping process. That, you know, if you have in-die a process that is heating the material, what impact have you seen with tooling life? Differences. Obviously, the tool has to be quite a bit different and designed in such a way for that. But just wanted to see your opinion on some of that.
Yeah, I'm trying to see, where did I have those pictures of the tool? There you go. Right. Yeah, the challenges, a few different challenges. Right. One of the challenges that's it's not a new challenge, but it's a challenge that we face differently, is the idea that we are designing these tools very different from the way that we used to design them before. First few times that I saw hot forming tools and I saw them from a distance, I thought for a while they were still prototypes in Kirksite because there was no coring, no visible coring. It didn't look like it was, narrow castings with ribs and things like that. But instead, it was these just giant monolithic blocks of material, and it really is a different way of having to design your dies, right? The die design rules and rules of thumb that we might have been carrying around for the past, 80 years worth of tool standards are pretty much going out the window because this is a whole new animal. As far as die life, I mean, they have to use appropriate materials for this punch, right? This punch, you can't just make this punch out of plain gray spheroidal cast iron because spheroidal cast iron, right? So the material like a GM248 or GM241, those materials won't behave appropriately if you're constantly heating them and cooling them every time they come in contact with a blank. So die design standards are certainly in flux as we're trying to adapt and adopt these heating and cooling channels throughout the tool. As far as the other challenges, the coating, right? There's an aluminized coating. We coat those blanks that we're going to stamp with the in hot stamping. You can't put zinc on them. If you put zinc on them, the zinc would just melt off at 900 degrees Celsius, right? It would just essentially vaporize. So those blanks are not zinc coated. They're not regular galvanized. We're instead using a silica aluminum type coating, which is highly abrasive. So what happens is you get these very abrasive tools with this aluminized coating, silica aluminum coating on it. You're taking it up to a high temperature and you're forming it against this punch, and we're seeing high wear conditions. And of course, it's a wear condition that you can't necessarily control very effectively with lube, or at least not the lubes we're used to using, because the lubes we're used to using don't behave the same at these, the material, the lube would have to perform from the top end of the temperature range to the bottom end of the temperature range. And most lubes that we might work with have optimal temperature ranges that are only maybe 50 degrees Celsius wide. It'll be good between 50 degrees and 100 degrees Celsius. But you're not going to find a lube that performs well from 400 degrees Celsius all the way up to 800, 900 degrees Celsius. That just doesn't make sense that a material would have a predictable performance over such a wide range of temperatures. So we get abrasive wear of these tools caused by this aluminum silica coating, and then we also get adhesive wear or galling, where the coating will start adhering itself to the die. Right, so we do end up having much higher mechanical maintenance of these dies. We got to polish them, we got to clean them more often. That also is a challenge. I seem to have lost Dean, and I was answering his question. What other questions or comments? Right. For Dean's company, this is another thing, is that in die sensing, you would want to have thermocouples in the die to know that your dies are being maintained at the appropriate temperature. Right. So that's when you think about our typical stamping environment, maybe we have some die telemetry built in, but maybe for load monitors or for knowing whether a punch is present or part present fixturing. But temperature sensing and temperature reporting is something people aren't used to having to do on a daily basis. What other questions or comments?
Well, you were talking about your sensing. I would think that the high temperature is going to affect all the other sensing that you have in there too.
Oh yeah, it's a different animal, right? We'd have to have and again, what's really interesting about the hot stamping for me is this range of temperatures we're talking about, right? We're talking about material just at its solidification, crystallization temperature, and then we're bringing it down to, when it's leaving the die, it's leaving the die somewhere between 80 degrees Celsius and 200 degrees Celsius. So it's just a broad range of temperatures that whatever sensing, whatever equipment we're using has to be flexible enough to be able to still behave properly through such a wide range of calibration environments. What other questions or comments? Snide remarks?
Very interesting.
It's hot. It's very interesting.
Definitely.
Yeah. But no, I've when I was, where was I most recently? Where I saw I was down in Ohio recently, and no, I was down in Brazil. When I was down in Brazil, I saw I was at Gestamp do Brazil, and there at Gestamp I was watching them, two different lines that were producing hot stamped materials, and they got probably about a 100 to 150 foot long conveyor belt passing through a series of furnaces, and when that blank comes out, it's piping hot, and they've got about maybe 4 to 5 seconds from the time it exits the furnace until they want that inside the press and forming metal before the material cools too much to cause different characteristics. So they have to plan everything for the instant it leaves the furnace until it gets loaded. How fast is the die closing? How long do we hold it closed? Are all things that have to be engineered well in advance and proven out in order to validate the product design and the product engineering decisions that they've made.
Yeah. Did I see something on one of the slides, and you don't have to go back and look for it, but where they're doing selective heating? Like maybe they're running, using an induction heating apparatus to just heat a portion of the blank?
Yeah, there's one of the ways that people in selective heating is actually really difficult to achieve right now, right? So there's very little industry-wide or industrial uses and applications of selective heating. They are, however, doing selective cooling. So what happens is they end up passing the whole blank through a giant, it looks like a giant pizza oven, right? The big conveyor belt pizza oven. So
Right.
they heat the whole blank up, and then at the tail end of that furnace, they've got a steel plate hooked up to a massive heat sink that will draw out a bunch of that heat right as it exits the furnace. And they'll use this selective cooling to try to cool the blank down. Now, there's a lot of R&D going on right now with exactly as you mentioned, Bob, of trying to use more selective heating techniques like induction. Right? So if you could build a better induction heating method, you could only heat the areas that you wanted to heat and just leave that blank cool. And when I was at the Technical University in Graz, Austria, they had built a proof of concept induction heating line, induction heating furnace. And rather than having when I mentioned Gestampt, Brazil, they had a 150-foot long radiant heat element furnace, right? So that whole oven's got to be heated up to that temperature, 900 degrees C. When with this induction furnace that I saw at the TU Graz, Technical University in Graz, they had a furnace that was actually only about, I want to say, maybe 15 to 20 feet long, so about 10% the overall length of a typical radiant heat furnace. And then they were using induction heating to heat just the areas that needed to be heated, and they were able to do this selective heating. There's a lot of potential, there's a lot of desire to do that, but no one has quite brought that out on an industrial scale yet. But that's one of the things that I would say that, yeah, in the future we should probably see people using a bit more induction heat. They had two patents that they were going for at that university. One was for the induction heating element design, and the other one was for the in order for the induction heating to work, they had to come up with a new way to move the blank through the line. So they had to design this new kind of innovative walking beam automation mechanism as opposed to a conveyor belt in order to maintain the appropriate induction behavior.
Right.
But yeah, it was really, really cool what they were doing. So yes, selective heating would be another way of achieving that tailored behavior of just the strength where you need it and not where you don't. Absolutely, good comment. Thank you, Bob.
Mm-hmm.
What other questions, comments, or snide remarks? Okay. Well, thank you everyone who stuck around till the end of this. I overstayed my welcome again, but thank you very much everyone for joining us in today's meeting. I look forward to taking a passenger seat next month, as Bob's going to teach me what I don't know and educate us all on stretch forming, its applications, its technology, and overview. Sound good?
That sounds good.
All right. Thank you very much, everyone, for coming in today. And I look forward to seeing you all in next month's meeting. Remember, anytime you guys do come up with any other ideas for future events, please feel free to send me or Brianne an email at the email addresses I listed here, so that we can get you in as a guest speaker, or we can find that guest speaker that you want to hear from to educate you on a new topic. Thank you.
Thank you.
All right. Hey, Bob, I don't know if you want to